In late July 1945, the sky above the Ando Seto Strait near the Kure naval arsenal fractured under the roar of American carrier aircraft. Their target was a massive floating fortress, and the mechanism of its destruction was brutally straightforward. A relentless aerial bombardment slammed into the steel decks, meeting a depleted, fragmented defense, yet still pushing through a hard curtain of anti-aircraft fire. Across the strikes on July 24th and July 28th, roughly 20 bomb hits tore through the superstructure and hull. The most devastating of these strikes were 5 direct impacts from 1,000-pound bombs. The detonations shattered heavy bulkheads, severed primary electrical lines, and ignited uncontrollable infernos deep within the armored citadel. This was the catastrophic end of the Imperial Japanese Navy warship Ise. The stakes of this violent execution extended far beyond the loss of a single vessel. When the fires finally burned out and the smoke cleared, an immense, shattered corpse of steel lay dead in the water, severely constricting and threatening to choke a vital navigational artery. To comprehend the sheer scale of the wreckage now choking the harbor, one must understand the unique and bizarre anatomy of this specific ship. The Ise was not a standard dreadnought. Measuring roughly 720 feet in overall length, she displaced an astonishing figure on the order of 40,000 long tons at full combat load. Her original design was purely focused on heavy surface gunnery, but the reality of a changing war forced a drastic architectural mutation. In 1943, Japanese planners ordered a radical hybrid conversion, part battleship, part aviation platform, born out of strategic desperation. Engineers physically cut away the 2 heavy aft gun turrets and their deep armored barbettes. In their place, shipwrights grafted a sprawling flight deck, a vast internal aircraft hangar, and 2 heavy catapult systems onto the stern. It was meant to carry and launch a limited air group while still retaining forward battleship firepower. This unprecedented structural modification fundamentally altered the weight distribution, the center of gravity, and the longitudinal shear strength of the colossal hull. The ship became an unbalanced amalgamation of heavy armor forward and cavernous, fragile aviation spaces aft. When the bomb strikes of July 1945 penetrated this compromised architecture, the results were definitive and terminal. The hangar deck became a massive void that could amplify blast overpressure from 1,000-pound detonations, turning the aft spaces into a brutal pressure chamber. Structural frames buckled, and the massive weight of the armored sections pulled against the weakened aviation stern. The Ise rapidly lost buoyancy as thousands of tons of seawater rushed through the ruptured lower hull plates. Struck in confined, shallow water, she dropped into the harbor mud and stuck fast. The shattered hybrid warship came to rest with about a 15-degree starboard list, much of her upper decks and ruined superstructure still visible above the tide. The violent sinking of this 39,000-ton Leviathan created an immediate, rigid blockade. The ship was no longer a weapon of war, but it had instantly become an insurmountable physical barrier for the reconstruction of the local maritime infrastructure. A standard marine salvage operation might typically involve sending down commercial diving teams to patch the ruptured hull, pumping out the flooded interior compartments to restore buoyancy, and finally towing the floating vessel to a secure dry dock for comprehensive repair or organized dismantling. However, the raw physics of this particular wreck, combined with the devastated post-war infrastructure, made traditional recovery methods effectively impractical. The Ise was securely pinned in the thick mud, geometrically distorted by the extreme force of the aerial explosions, and simply too massive to drag through the shallow depths. The engineering teams tasked with surveying the ruined harbor faced a profound logistical nightmare. They had to logically deduce how to completely erase a localized mountain of fractured high-tensile steel without the use of standard heavy-lift dockyard equipment or massive floating cranes. The ship was dead, yet its wreck still sealed the channel. The geometry of the resting wreck dictated an unforgiving physical reality. When the massive steel hull slammed into the seabed of the strait, it did not plummet into the abyss or capsize completely. Instead, it was caught in a zero-clearance trap. The water was exceptionally shallow, meaning the vessel bottomed out violently while its main deck was still awash. The immense displacement of the battleship meant her keel sank deep into the thick, cohesive harbor mud. She settled for good, heeled roughly 15 degrees to starboard. This precise angle of repose created a highly unstable equilibrium. The center of gravity, already thrown off axis by the destruction of her upper works, shifted drastically to the starboard side. Half of the shattered main deck remained exposed to the air, while the lower engineering spaces and the entire starboard torpedo blister were deeply buried in the suffocating silt. It left the wreck in a cruel limbo, too wet to dismantle cleanly, too exposed for blast-clear solutions. It was locked in an agonizing threshold between the surface and the seafloor. The sheer mass of the warship was actively tearing itself apart as it rested in the mud. The foundational strength of any large vessel relies on its continuous hull girder, acting as a single, uninterrupted beam across the water. But this hull was already living on borrowed strength. The hybrid conversion created a harsh structural transition. Heavy armor and turrets forward, lighter aviation spaces aft. Under bombing damage and uneven settling in shallow mud, that boundary could become a brutal stress riser. Severe deformation and possible cracking appeared near the forward edge of the flight deck as the armored forward mass sagged one way and the hollowed stern reacted another. Longitudinal plating along the upper hull began to tear under the twisting loads. That fracture effectively split ice into two armored bodies, barely stitched together by torn steel. The 15-degree starboard list exacerbated this critical failure at every moment. Because the hull was leaning heavily, the twisting force on the fracture point multiplied continually as the tides shifted. If any marine engineer attempted to attach heavy lift pontoons or apply external buoyancy to right the vessel, the unequal distribution of mass would cause the remaining steel tendons connecting the two halves to violently shear. The forward section would roll one way and the stern would twist another, potentially collapsing inward on any technical teams attempting to work inside the flooded compartments. The structural hull fracture turned the dreadnought into a lethal, unpredictable load that could not be lifted intact. Furthermore, the dense harbor mud exerted a tremendous physical grip on the fractured hull. The breakout force needed to overcome seabed suction on a deeply buried, flat-bottomed hull can vary wildly and can far exceed the wreck's effective underwater weight. Even if the hull girder had been perfectly intact, breaking the suction on thousands of tons of steel would require lifting forces far exceeding the capacity of any floating crane available in the region. Because the spine of the ship was completely severed at the flight deck margin, applying massive vertical lifting force to overcome the mud suction would merely rip the ship completely in half and drag the broken sections deeper into the silt. Patching the ruptured bulkheads to pump the internal spaces dry was equally futile. The sheer volume of missing steel from the bomb strikes, combined with the catastrophic structural split across the ship beam, meant watertight integrity was a physical impossibility. The ocean flowed freely through the devastated engineering spaces, equalizing the internal pressure and pinning the dead weight firmly against the ocean floor. The math was merciless. The wreck could not be refloated, and it could not be dragged free. If the channel was to reopen, Ise had to be cut apart where she lay. The standard protocol for a naval casualty of this magnitude demands a massive graving dock and heavy marine towage, but the Harima Zosen Corporation inverted this doctrine completely. When the commercial firm was awarded the massive salvage contract to clear the Ando Seto waterway, their engineering team immediately discarded any concept of moving the wrecked battleship. The sheer mass of the fractured dreadnought and the extreme lack of deep water port infrastructure left them with a binary choice. They could either leave the Iron Mountain permanently entombed in the navigational channel, or they could execute a highly dangerous operation to dismantle the hull where it lay. This institutional decision forced a radical shift in logistical planning. Because the hull was permanently locked in a zero-clearance trap, the engineers had to bring the heavy industrial capacity of a terrestrial shipyard directly out into the ocean. The formal operation officially commenced on October 9, 1946. The immediate obstacle was power. A sunken 39,000-ton steel structure is a dead zone, completely devoid of the massive electrical current and hydraulic pressure required to operate heavy cutting equipment, commercial salvage pumps, and industrial lighting. The warship rested too far from the shoreline for standard cable drops, and bringing a fleet of floating generator barges alongside the wreck would crowd the already narrow channel and create severe hazards during foul weather. To solve this, the Harima Zosen teams built a temporary pontoon accessway, an improvised floating work road, linking the wreck to shore power and supplies. This method fingerprint became the defining technical achievement of the entire setup phase. Instead of relying on vulnerable boats to ferry crews, tools, and limited power to the site, they built a rigid physical bridge connecting the dead battleship directly to the local shore grid. It was built to carry far more than men. The engineers chained together heavy steel pontoons and reinforced timber decking to span the gap between the tidal mudflats and the heavily listing hull. This was not merely a footbridge for scrap metal workers. The causeway was heavily overbuilt to support the immense weight of thick industrial power cables, heavy-duty steel piping for high-capacity dewatering pumps, and a continuous flow of massive oxygen and acetylene gas lines required for the cutting torches. By hardwiring the wreck to the mainland, the shore teams could safely run high-voltage, alternating current across the water without exposing mobile generators to the constant risk of swamping or fuel exhaustion. The umbilical delivered a relentless, unlimited supply of energy and pressurized gases directly to the shattered main deck. Constructing this physical link required precise marine geometry and constant adjustment. The causeway had to be flexible enough to absorb the daily tidal shifts of the harbor, yet rigid enough to carry hundreds of salvage workers and the heavy extracted material safely back to land without buckling. The physical interface, where the floating bridge met the starboard leaning hull, presented a severe friction point. The engineers had to weld custom attachment brackets to the jagged armor belt to prevent the causeway from tearing loose during heavy swells. Deep anchors and spring lines kept the pontoons from slewing, so the power and gas runs stayed straight and safe. If the floating bridge snapped under the changing tide, the heavy electrical cables could sever, instantly electrifying the shallow water and sparking catastrophic fires among the volatile cutting gases. Once the physical bridge was locked into position against the starboard armor belt, the wreck was effectively transformed into an artificial peninsula. The salvage teams had successfully routed terrestrial power into a dead, flooded marine environment. Staging was complete. The wreck was lit, powered, and hard-tethered to shore. The shore-based pumps were primed, the electrical grids were live, and the cutting teams were standing by on the flooded main deck. With electrical power flowing to the dead ship, the salvage teams prepared to alter the delicate buoyancy of the massive hull. The systematic erasure of a deeply embedded dreadnought requires an agonizingly slow and highly calculated sequence of vertical subtraction. So the crews began cutting her down in place, piece by piece. This reverse engineering deconstruction mandated that every piece of heavy armor, deck plating, and internal machinery be manually cut away while the ship remained pinned to the ocean floor. The workers began at the highest points of the ruined pagoda mast and the shattered flight deck, using heavy oxygen and acetylene torches supplied by the umbilical supply line. Severing these massive steel sections required immense heat and extreme physical endurance, as the crews worked directly over open, flooded voids. Every ton of high-tensile steel removed from the upper works fundamentally altered the delicate physical balance of the wreck. A battleship is designed with heavy top weight, counterbalanced by massive lower hull displacement and deep keel structures. As the cutting team systematically eliminated the superstructure, the flight deck elevator mechanisms, and the upper armored barbettes, they erased the top heavy mass that had forced the ship into the mud. However, this vertical subtraction was highly dangerous due to the compromised shear strength. The catastrophic break across the ship beam meant the two halves of the hull were reacting independently to the changing weight distribution. If the forward armored section was lightened too quickly while the flooded stern remained heavy, the remaining steel tendons connecting the fractured sections would violently snap. The unpredictable torsion could easily collapse the internal bulkheads, crushing the salvage teams working in the deep lower galleries. Therefore, the cutting schedule had to perfectly mirror the fractured geometry of the wreck, removing mass symmetrically across the immense crack in the hull. To prevent a sudden, lethal shift in the mud, the engineers used selective dewatering wherever any compartment could still be isolated. This was never an attempt to refloat the ship. It was stability control, keeping the list from snapping the worksite and keeping the fractured halves from reacting differently as weight came off the top. The rhythm was deliberate. Cut away a heavy block, open a new void, drop in pumps, seal what could still be sealed, and pull out only enough seawater to replace the steel just removed. Done right, the wreck stayed in a forced equilibrium, neither sinking deeper into the mud nor grinding its broken sections together. Month after month, The towering profile of the hybrid warship was ground down to the waterline. The heavy gun turrets, the shattered aircraft hangars, and the massive armored belt were systematically carved into manageable blocks and hauled away. But as the immense upper structures disappeared, the remaining lower hull, deeply entrenched in the mud, became dangerously buoyant and increasingly difficult to manage. The engineers had successfully stabilized the descent of the wreck, but to reach the final, deeply buried prizes at the very bottom of the hull, they could no longer rely on maintaining a stable platform. As the superstructure vanished, the ship's center of gravity shifted drastically, forcing the engineers to purposely destabilize the remaining lower hull. The mechanism required to extract the deepest, the most heavily entrenched components of a sunken dreadnought involves deliberately destabilizing the very hull the salvage team spent months securing. The engineers had successfully sheared away the massive armored citadel, the complex internal machinery, and the shattered aviation stern. What remained was a heavily buoyant, hollowed-out lower steel trough resting precariously in the thick harbor mud. The center of gravity had completely inverted. The massive top weight was gone, leaving the buoyant lower voids pulling aggressively upward against the immense seabed suction. The remaining structure was nothing more than a shallow, flooded steel basin, severely weakened by the continuous subtraction of its heavy internal bulkheads and thick transverse framing. The most valuable strategic materials remaining within the wreckage were trapped at the extreme aft end of the ship. Completely submerged and heavily buried beneath the thick mudline, the heavy propulsion shafts culminated in immense, solid manganese bronze propellers. For a nation rebuilding, those manganese bronze screws were a primary prize and a financial driver of the entire job. This base material recovery required precise metallurgical separation. Bronze does not corrode like high-tensile steel when exposed to harsh saltwater environments, and its extreme density and material purity made it a highly prized target. However, accessing these massive components presented a severe geometric challenge. The severe starboard list had driven the starboard side screws deep into the suffocating silt, and locking them under thousands of tons of wet earth and shattered steel plating. To reach these buried components, the salvage crews had to free the stern from mud, wreckage, and collapsed plating. Rather than trying to lift the ship intact, they combined excavation, careful cutting, and controlled pumping wherever it remained feasible to reduce the seabed's grip and expose the shaft lines. Inch by inch, the mud let go. The stern geometry emerged enough for the propellers to be accessed without gambling on a dramatic, uncontrolled roll of the remaining structure. The thick harbor mud sloughed away, revealing the thick steel propulsion shafts and the massive, gleaming manganese bronze blades. Heavy cutting teams immediately descended onto the newly exposed lower hull sections. They rigged massive chain hoists and heavy block and tackle systems to the remaining solid framing of the stern. Using extreme high-temperature thermal torches, the workers meticulously sliced through the thick, solid steel propulsion shafts. They effectively amputated the immense bronze screws from the dead internal machinery of the flooded engineering spaces. Once the final cuts were made, the heavy winches strained under the immense load, hauling the massive alloy castings up and out of the mud trap. The gleaming metal was carefully transferred onto waiting transport barges, destined to be melted down and repurposed for the massive national rebuilding effort. The most valuable metals were severed from the shafts, leaving nothing but a flooded shell. Between the late 1945 aftermath and the summer of 1947, the immense steel corpse of the hybrid dreadnought transitioned from a wartime casualty into a navigational hazard marked for removal. Before the commercial dismantling crews fully committed to heavy cutting, post-war U.S. naval technical teams, including the Naval Technical Mission to Japan, compiled assessments drawn from Japanese records, interviews, and limited inspections of damaged ships and facilities. Their work helped establish a technical baseline of what had happened at Kure and what condition the wrecks were in, closing the military chapter and clearing the path for commercial salvage. Once the intelligence officers completed their extensive surveys and departed the site, the relentless industrial machine of the commercial salvage firm consumed the wreck. The clipboards went quiet and the cutters took over. Over the subsequent months, the massive silhouette of the dead Leviathan steadily disappeared from the shallow harbor. The ultimate operational goal was not merely to reduce the hazard of the wreck, but to completely annihilate its physical footprint and permanently reclaim the vital shipping lane. The continuous daily transfer of severed steel from the ocean back to the mainland represented a massive logistical triumph for the engineering teams. The successful extraction of the heavily buried base materials provided a crucial, massive influx of high-grade structural steel and rare alloys for a devastated nation, desperately attempting to rebuild its shattered civilian infrastructure. Through the cold winter and into the sweltering summer, they cut the Iron Mountain down past the waterline and into the mud, until nothing remained to snag a passing merchant hull. The crews painstakingly swept the muddy harbor floor, ensuring that no jagged shards of heavy armor or torn internal bulkheads were left hidden beneath the water. The final confirmation of a clean seabed was just as critical to the post-war recovery as the removal of the towering superstructure. Erasing a 39,000-ton dreadnought without the aid of a commercial dry dock required an astonishing level of sustained physical endurance and mechanical precision. Every heavy ton of steel hauled away meant a fractional increase in the safety and navigability of the local strait. The monumental in-place salvage operation officially concluded on July 4, 1947. On this definitive date, the final jagged sections of the deeply buried, heavily armored keel were severed from the thick seabed and hauled ashore. The immense physical blockade that had choked the shallow water for 2 years was finally and entirely eliminated. The local navigational artery could finally be reopened with the wreckage hazard removed, restoring safe passage through the strait. The completely severed remains of the massive warship had been systematically erased from the earth. The highly dangerous, meticulously calculated undertaking had achieved total success.